Hello everyone. Today we will take subtraction more seriously. So just to review the last part of our lecture on addition and subtraction. What we ended up last time was two interpretations of subtraction. So we viewed subtraction in two different ways. The most obvious one is like take something away from a whole. You have a group of objects and you want to take a few away from it. We can also call it remove, delete, and so on. Another interpretation was the whole part interpretation. So here it implies physical removal of objects from a group. Here you don't remove anything, you just have a whole and you presumably know one part of it, let's say in that whole, you know the number of objects of one type, so you call it one part, and then there are objects of another type, and you say, okay, that's a question mark. So how do you work that out? That turns out to be the whole minus the part. So here you are doing everything conceptually, there is no removal or deletion. And as I told you at the end of that lecture, these two interpretations are limited because they do not allow us to answer questions related to comparison. Subtraction arises in situations where we want to compare things. So let me remove this. It will also turn out that these two cases can be seen as special cases of that new interpretation. So let me give you a few examples. So imagine you want to compare objects. Actually, I would say the number of objects or count of objects, and it's important, of two types. Now, one thing is very clear, you must remember that we are talking about objects of two types, and one more thing is that these objects are not necessarily physical. Yeah, you can think of any concept, yeah? A conceptual object, an abstract object. We'll see example. Let me give you a few examples. So say you are earning, so you have a gain, and you are losing, you have a loss. So you can say the number of gains, or maybe you can say a number which represents the gain, yeah, you are gaining something, and a number representing the loss. You want to compare these two, so you can say, okay, subtraction will give me the difference, this will now be the. So a direct outcome of comparison will be what we call a difference. So we see a difference as the number which we obtain as a result of this subtraction, where you subtract one type, the number of one type of objects from the number of another type of object. You can also say the number of steps you take forward. Let's say you're walking. So you see, we're not talking about physical objects all the time. Yeah, this is an abstract concept. Number of steps you take forward minus the number of steps you take backward. This will now give you another difference. Yeah. Maybe one more example. You know electrons and protons. Yeah? So I can say, and you know they differ by an important property we call charge. So the electrons and protons, they have opposite charge. So I can say in a lump of matter, if I have the number of protons minus the number of electrons, it will give me a difference of charge. And I can give you countless examples. Now, it is very easy to conceive situations where this number from which you are subtracting this number, you typically assume this to be larger than that so that you get a positive number. Yeah. But sometimes you have a situation where this is small and this is large. So if I give you a few examples, now, I mean, the examples will be more generic, so I'll not be repeating these cases. You can, you can fill this list with your own example. Let me just give you some numerical cases. So I can say 2 minus 1, yeah. So if I take 2 steps forward and I take 1 step backward and I want the difference, this is obvious. But you could also be interested in 1 minus 2. Yeah? 1 step forward, you take 2 steps backward. Yeah? So, I mean, one way of resolving this is that, okay, in both cases I can say, okay, here I have just, the difference is 1, here the difference is again 1, and I'll just label it. Yeah? I'll label this as forward, and I'll label this as backward. But what if I don't want this qualification? Yeah. It would be very nice that if this is viewed, as a difference, and a difference is represented by a number, I would like to have a number which represents this difference so that I don't have to qualify this, because these cases, each time writing this down may not be convenient. And then you will have to rely on the different examples. We want a generic answer. So why would I, it's easy to imagine that 2 minus 1 is 1, but why would you like to define a number of this type, where you subtract a larger number from a smaller number? If you go with those first 2 interpretations, removal and whole part, this doesn't make sense, because you cannot imagine a whole of size 1 where you can take, where you imagine that, okay, a part of it is of size 2. No, yeah, that doesn't make sense. Similarly, you cannot remove 2 from 1. But if you view this as a change or a difference, you see, because a difference represents a change, this in isolation may not make sense, but let me tell you, you change something which is already there. Similarly, when you want to know the difference, that difference is seen in something. Yeah. So to justify why it will make sense to have a number not only for this difference but also for this difference, let me give you another very interesting example. And this is actually the punchline. So say I start from the number 7. This could represent any situation. It could represent 7 objects, it could represent 7 apples, it could represent 7 steps you have taken forward, and so on. So what can I do with this? I can add to this 2, and after that I can subtract 1, yeah, and I can see, okay, the net effect of these two changes. So first I added 2 to 7, and then I subtracted 1 from the result. This is the same as 7 plus 1, because I know this is 1. Yeah. Now this one is different from this one, because this one is a count and this one is a difference. Yeah, but they are numerically the same, different meanings. What if I do this? What if I subtract 2, yeah, and then I add 1? What is this? Now, because you know it, in addition, when you are adding and subtraction, it doesn't matter which one you do before, commutative, as you call it. This is the same as 7 plus 1 minus 2. It doesn't matter whether I add 1 and then subtract 2, or I subtract 2 and then add 1. The net result will not change. I can see that pattern again. So 1 minus 2 may not make any sense in isolation, but it makes perfect sense when you see this as a change made to 7, and you see you are using the sign addition. So if I see addition as a change, this is a legitimate number. The only thing is that I need to know what I am doing. The net result of this is what? This in isolation makes no change, but the net result of this 1 minus 2 is that because you are adding 1 and you are subtracting 2, the net change you are making to this is what? Is you are subtracting 1. And because this 2 is actually 2 subtractions. You can see this as minus 1, minus 1. Yeah, so this plus 1 and this minus 1 is like no change. Yeah, I can actually do this. This is the same as 1 minus 1 minus 1. Yeah, like minus 2 would mean that I am subtracting 1 and then I am subtracting again minus 1. And you see plus 1 and minus 1 leaves it unchanged. So the net result of this is 7 minus 1. See the effect. 1 minus 2 can be seen as a difference, and I can call it a new number, and I have to invent. Actually, I'm not inventing anything. Let's say the one who came up with these ideas, they must have come up with a notation. So let's say if I see this as a legitimate number, the effect of adding that new number to 7 or any other number is the same as if you are subtracting 1. So addition has an equivalent subtraction. Adding this number is the same as subtracting some number, and you see that number is positive, you know it. Yeah? So if I now rewrite this, you will see a pattern. Yeah? If I start with 7, and if I have this number, it is the same as 7 minus 1. Yeah? Let me give you another example. Yeah? I add 2 and I subtract 3. Yeah? The net effect is again subtraction of 1, because 2 in this, 2 subtractions in this will cancel out 2 subtractions, because adding 2 and subtracting 2 will leave this unchanged. So this is the same as 7 minus 1, which also means that although I write 2 minus 3 here or 1 minus 2 here, these two are in fact they represent the same changes, the same differences, you see, because there it doesn't change. In fact, in both of these cases I can, because this 2 can be written as -1, yeah, so this 1 will get cancelled out, and similarly this 3 can be broken down to 2 and 1, and then you see, so the net effect of this can be this. I can simply write 0 minus 1 because these two are equivalent to adding 0, which means not doing anything, and subtracting 1. See? Adding 0, subtracting 1. And you will now see easily why I wrote that answer in the first place. So there is now a pattern. You have defined a new number, yeah, which in isolation makes no sense, but in addition, when you see this as a change or as a difference, yeah, by comparing 0 with 1, you know what this does. The only thing you need to remember is that adding this new number is the same as subtracting. And you see, this one is this one. And now I can continue with this. I can now come up with a new idea. I can now imagine this number. Instead of 1, I can write 2. So the effect of adding 0 and subtracting 2, because 0 will not do anything, and subtraction will have to be done. Yeah? So you see, 0 minus 2 can be seen as a new number. And 0 minus 2 is such that adding it has the same effect as subtracting 2, because 2 is very well understood. This is what we mean by negative numbers. Yeah? Now, why are they called negative number? Because this is the minus sign, we call it plus and minus. And we know that 0 is something which doesn't change any number. So it doesn't really matter whether you write this 0 or not. So you can think of this as -2, because you see, writing 0 does not give you any information. And similarly, this 0 minus 1 can be viewed as -1. That's the main idea behind negative number. So if I now remove this, I've introduced you to the concept of you want to compare things. Yeah, that comparison is conceptually represented by some difference, and you represent that difference here by subtraction. Yeah? And there you have two cases. So if you have subtractions of this kind, like 2 minus 1, yeah, 1 minus 0, 3 minus 2, 4 minus 3, and so on, all they give you, all these subtractions, they all represent the same change, and that we can call +1. Now this +1, although it is 1, you should not confuse this 1 with the one we used for counting. Yeah? Because there you are not comparing anything, you are just counting objects. This 1 is a result of comparison. So all these comparisons lead to the same number 1. And this 1, although numerically it is equal to that 1, it has to be seen as a difference. Yeah? And you can interpret it in your own application. And if it is of this type, where you subtract a larger number from a smaller number, so 1 minus 2, 0 minus 1, 2 minus 3, 3 minus 4, all these represent another number which we will call -1. You see, -1 actually it is that 0 minus 1. Because this 1 minus 0 is the simplest of all, and it doesn't matter whether you write 0 or not, so we call it +1. And this 0 minus 1 is the simplest of all these cases, and all they are equivalent, and it doesn't matter whether you write this 0 or not, so we just call it minus 1. So this is one type of difference, this is another type of difference. So, and interestingly, what if these two numbers are the same? What if I have 1 minus 1, 2 minus 2, 3 minus 3, they all represent no change. So what do we write? 0. Now, this 0 is also different from that 0. The 0 we defined earlier represented the size of the empty set, because it literally represents nothing. Here, it is not nothing. When you say nothing, you only say that the difference, there is no difference. It doesn't mean that there is nothing. There are things which you are comparing. You are comparing 1 with 1. Here you are comparing 2 with 2. Here you are comparing, you must have two things and you must have two things. So all these could correspond to physical situations. And here, this 0, so now you have found a new interpretation of numbers. 0 could represent the size of nothing, but it could also represent a difference of equal numbers. Similarly, positive numbers 1, 2, 3 can be viewed as counting numbers, like when you are counting objects, but that same positive number, and same goes for 2 plus 2. Yeah? If I replace this with 2 minus 0, 4 minus 2, 6 minus 4, they all will be represented by plus 2, a change of plus 2, a difference of plus 2. Similarly, I can write 1 minus 3, 0 minus 2, yeah? 2 minus 4, they all represent a change of minus 2. So now we have discovered a new set of numbers which we will call integers. Integers should not be confused with natural numbers, because natural numbers are counting numbers. Integers are not counting numbers. Integers represent differences, changes. Essentially, in today's lecture, we have discovered a new set of numbers which represent changes or differences. So we will call that set the set of integers, as opposed to the set of counting numbers or the natural numbers. So these integers will always, they will represent differences. So 0 would represent no difference or no change, plus 1, a change of plus 1, 2, 3. Similarly, minus 1 will represent a change or a difference of minus 1, minus 2, and so on. Yeah? And interestingly, the set of natural numbers appear as a subset if you remember to change the meaning of it. Yeah? So if you want to see this as counting numbers or natural numbers, you will change the meaning. You will view them as counting numbers. Numerically, they are the same. In the next lecture, we will begin with arithmetics with integers, because arithmetics with integers, we have to be very careful with that, because the meaning of addition, subtraction, and multiplication, the reason I delayed multiplication was because I wanted this concept of integers before we get to multiplication. So stay tuned.